At 32 years old, Sabrina Pasterski is cited by global media outlets as one of the most brilliant scientific minds of the last century. Specifically, the press frequently labels her the new Einstein, a comparison meant to signal a rare, generational intellect. Pasterski rejects the title. She finds the comparison inaccurate and pushes back against the archetype of the lone genius that the label implies. Her perspective is rooted in the practical world of an engineer. She evaluates theoretical physics based on its potential for real-world application, looking at her research through the lens of a company that might eventually implement her labor. To follow her logic, we have to treat the universe as a mechanical problem, a system with specific functional parts that must be tested and refined like any other piece of machinery. When she was 9 years old, Pasterski shared a common childhood wish. She wanted a flying broomstick like the ones in the Harry Potter series. Her father, an electrical engineer and lawyer, responded with a more grounded alternative. He enrolled her in flight lessons at a local airport, steering her toward actual aviation. By age 14, she had transitioned from flying to building, successfully constructing her own aircraft from scratch and eventually piloting it herself. However, her entry into the professional aerospace world was a disappointment. She found that the industry had moved away from physical construction, with most engineers spending their time writing software code for drones. Seeking a more rigorous structural challenge, she pivoted. She took that builder's mindset and applied it to the most complex architecture in existence, the mathematical laws of the universe. Today, that work centers on quantum gravity and the mechanics of black holes. In engineering terms, modern physics is currently stalled because it is relying on two blueprints that do not fit together. This diagram represents general relativity. It is a macro-scale blueprint that treats space-time as a smooth, predictable fabric that curves around stars and planets. But as the camera zooms in to the atomic level, that smooth fabric disappears. We enter the world of quantum mechanics, where particles behave with a chaotic, jittery unpredictability that ignores the rules of the macro world. Pasterski is working to build a unified mathematical model where these two systems finally interlock, resolving the friction that currently leaves physics with two conflicting stories of reality. She approaches this by sifting and sorting through mathematical theories, a process of elimination similar to checking physical aircraft components for a proper fit. Her contribution is the application of this systematic assembly line rigor to the abstract equations that define our world. This friction extends beyond the equations and into the professional structures of the scientific community itself. Early in her aviation training, she noted a stark imbalance in the industry, an environment where women were often present but rarely occupied technical or leadership roles outside of secretarial work. In the academic world, she encountered a different pressure, a highly visible effort to spotlight women in STEM as symbols of progress. Pasterski argues that this focus can backfire. When institutions prioritize demographic visibility over individual output, it can create a sense of resentment among peers and leave the researchers themselves feeling like their presence is a performative gesture rather than an earned achievement. For her, the goal is simple: to be recognized for the objective quality of her physics, rather than her popularity in the media or her status as a demographic outlier. This focus on objective output leads to her primary critique of her field. Modern academic physics is too isolated, with researchers often working in complete solitude. She points out that while the tech sector focuses on scaling and applying discoveries, academia often lacks the framework to turn its scientific achievements into something that can lead to tangible change. To bridge this gap, she advocates for a shift toward the collaborative, fast-paced environment of a startup. She identifies the rise of large language models as a catalyst for this change. These tools analyze data at a volume no single person can track, requiring a team-based approach to manage and interpret the findings. Because these new technologies require diverse technical oversight to be effective, their adoption will likely end the era of the solitary researcher, forcing the field to adopt a more collaborative, project-based structure. For decades, science was defined by figures like Stephen Hawking, the solitary genius whose individual mind seemed to hold the secrets of the cosmos. Pasterski is pointing toward a different future, where scientific discovery is a collective effort, driven by builders using advanced tools to solve cosmic problems as a team. Her advice to those entering the field is to take an active role in this evolution. If you don't feel in place, change it. The next breakthrough likely won't come from a new Einstein working in isolation. It will come from builders who are willing to take the system apart and reconstruct it, whether that system is an airplane, a scientific institution, or the laws of physics themselves.